Welcome back, and welcome to the first of 8 lectures in which we'll explore the basic scientific principles governing the behavior of structural elements, structural materials, and structural systems. Now, at this point, you may be wondering why we're doing science in a course about great structures. To address this question, I'd like to spend just a few minutes discussing, first, the role of science in engineering, and then the role of science in this course specifically. Last lecture, we talked about the development of engineering through 2 great historical eras. The era of empirical design, which began in distant antiquity and progressed all the way through the Renaissance, and the era of science-based design, beginning with the scientific discoveries of the 1600s and continuing to the present day. And we saw that 4,500 years of empirical design produced many magnificent structures without the aid of any scientific methods at all. Unequivocal proof that science isn't actually essential for engineering. Nonetheless, it's instructive to compare one of the most ambitious structures of the empirical era, the magnificent 142-foot diameter dome of the Roman Pantheon, by far the largest of antiquity, with a modern equivalent, the 710-foot diameter Houston Astrodome. It's 5 times as large. Based on this comparison, we really can't help but recognize that science-based design methods combined with modern structural materials have opened up vast new realms of structural possibility. When engineers had only empirical methods available for design, each new design was basically based on what had worked well in the past. It was really only possible to do minor incremental changes from what was already known without incurring fairly significant risk. But with modern scientific tools at their disposal, today's engineers aren't bound by precedent. They can look to the future. They can work with any conceivable structural configuration. They can model that structure mathematically. They can predict how it'll respond to loads, and then they can design it so it can carry those loads safely and efficiently. In effect, scientific tools allow modern engineers to predict the future with confidence, even if that future bears very little resemblance to the present or the past. The result is the potential for structures of far greater size and complexity. Now, having said that, I should add that today's near universal use of science-based methods hasn't diminished the importance of experience in engineering design. Many of the modern era's greatest structures, for example, Robert Maillart's beautiful Salganitobo Bridge in Switzerland, used fundamentally empirical design approaches that were informed by scientific principles, but they were really guided by experience, by observation, and by experimentation. And on the other hand, some of our greatest failures, for example, the infamous collapse of the Tacoma Narrows Bridge in Washington State due to wind-induced vibration, resulted, at least in part, from over-reliance on science and inadequate attention to past experience. We'll look more at this case in Lecture 16. Still, engineering as we know it today simply couldn't be performed without science. And just as scientific principles are vitally important tools for modern engineers in practice, so these principles are also a vitally important component of this course. There are 3 reasons why it's worth your time to invest in learning in the science of structures, and more specifically in the science called engineering mechanics. First, science provides a sort of a shortcut to understanding. If we wanted to learn how columns work, one approach might be to build a whole lot of columns, hundreds of columns, and then take them into the laboratory and test each one and observe how it behaves under load. Observe how differing geometry and different materials affect the strength of those columns. And then based on all that data, try to generalize some sort of overall conclusions about how columns work. That's one approach. Or we could glean the same level of understanding from a 15-minute introduction to basic scientific principles governing column behavior. Given our short time together, I think we'll adopt the latter approach. Second, science provides universality. As engineers of the empirical era knew well, experience really only equips us to understand structures that are more or less similar to the ones we've seen before. But an understanding of scientific principles allows us to understand and even to design any structure, even if we have no experience with that structure previously. And this is true even for the empirically designed structures of the ancient, medieval, and Renaissance eras, because the science is always there, manifested in the actual behavior of the physical structure. And then finally, science equips us to solve problems quantitatively, rather than simply gleaning a qualitative understanding from behavior. And often, that sort of quantitative analysis provides higher levels of insight that simply aren't possible with qualitative methods. We'll see a number of examples of this phenomenon over the next couple of lessons in this course. So, let's embark on our journey through the wonderful world of engineering mechanics, a branch of the physical sciences that deals with the effects of forces acting on bodies. Ah, two new terms. When I use the term body, I'm simply referring to some sort of a physical object. I wish I had a physical object to show you. Oh, look, here's one. This is a 2-pound piece of steel bar. When I say that it weighs 2 pounds, what I'm really saying is that there's a force of 2 pounds that's being applied to the object in the downward direction. So what's a force? Well, as you might recall from your high school physics course, a force is a push or a pull applied to an object. Force always has both magnitude and direction. When we draw a force, we always represent it graphically using an arrow. I wish I had an arrow to show you. Oh, wait a minute. Here's one. So, when we apply a force to an object, we represent it as an arrow, and the real purpose of the arrow is to designate the line of action along which the force is applied, and that's critically important to being able to understand how forces work. A force also has magnitude, which is expressed in either pounds or tons or a similar unit in the US system of units, and expressed in newtons in the metric system. This particular force, again, has a magnitude of 2 pounds, which is equivalent to 9 newtons metric. Now, the use of newtons as a unit of force is a most appropriate way of honoring Sir Isaac Newton, whom we'll meet in just a few minutes later on in this lecture. In this course, we'll be relying primarily on the US system of units throughout the course, really just for the sake of simplicity. So, back to engineering mechanics, the study of forces acting on bodies. It sounds kind of mundane, but actually mechanics is a fascinating subject because it tells us important things about how the physical world around us actually works. Leonardo da Vinci, the quintessential Renaissance man, wrote the following in one of his notebooks. Mechanics is the paradise of mathematical science, because here we come to the fruits of mathematics. So, welcome to paradise. The fruits of mathematics are forbidden no more. Paradise is a wonderful place, but to make the most of it, you need to be able to find your way around. So I'd like to spend a few minutes in this lecture building a roadmap that'll help us navigate our way through the mechanics concepts that we'll be exploring in detail over the next few lectures. To illustrate this roadmap, I'd like to use this particular grade structure. It's the Chuteau Bridge over the Missouri River at Kansas City. Not only is this wonderful old railroad bridge a beautiful example of 19th century industrial technology, it's also an excellent teaching tool for basic mechanics concepts. So we'll be coming back to it a number of times over the next couple of lectures. Our roadmap shows the major concepts that are involved in the analysis of a structure. Let's build it a step at a time. First, structural analysis always begins with external forces. And external forces come in two flavors, loads and reactions. Let's use a physical model of the Chuteau Bridge to give these concepts a little bit more physical meaning. Here's our model of the Chuteau Bridge. And the actual structure, the actual railroad bridge structure, experiences two principal kinds of loads. They're called dead load and live load. Dead load is load that is permanent and unchanging, and the most important type of dead load is the self-weight of the structure, its own mass. Live loads are called live loads because they vary in both magnitude and location. So typical examples of live load for a railroad bridge like this would be the weight of heavy trains crossing the span, as well as a variety of different kinds of environmental forces. For example, when the wind blows on the side of the bridge, it exerts pressure that constitutes wind loading. When snow falls and accumulates on the deck of the bridge, it adds weight, which is another form of live load. We'll be talking about loads much more comprehensively in a later lecture, but you get the general idea from this quick summary. Now, my physical model bridge happens to weigh 2 pounds, so that's the dead load associated with this structure. And to simulate the live load of a locomotive crossing the span, I'm going to take this steel weight, which weighs 3 pounds, and I'm going to hang it precisely in the middle of the bridge at mid-span. Okay? So those are loads. The second type of external force is the reaction, and a reaction is defined as a force that's developed at a support in response to those applied loads. A support is just a physical connection between the structure and its physical surroundings, its foundations. So the supports are located right here at this point and at the equivalent point on the opposite end of the bridge. It's important to recognize that reactions are caused by loads. We're going to explore this process and understand how it happens in just a minute. But first, let's move on to the next step in our roadmap, internal forces. Internal forces are caused by external forces, but internal forces occur within the individual structural elements. We've already talked about the two principal types of internal forces. They are tension and compression. When I apply a load to the Chuto Bridge, tension and compression are actually generated within all these individual structural members of the bridge. You can't see that, though. What you can see, though, is that when I apply load to the bridge, it does bend downward slightly. It bends downward. It turns out that a truss is very similar to a beam. And you can see that when I bend this beam, both compression and tension are occurring within the beam. When I bend the beam, the top surface gets a little shorter, the bottom surface gets a little longer, and so we have compression in the top, tension in the bottom, which occur as a natural consequence of bending or flexure. It turns out that trusses work exactly the same way. So when we apply this large load out here at midspan, we're actually generating a significant amount of compressive internal force in all of the members that run along the top of the bridge, and a significant amount of tensile or tension internal force along this member that runs the entire length of the bottom of the bridge. Okay? Next step in our roadmap is stress, which is defined as a measure of the intensity of internal force. Stress is actually a distributed force. It's distributed over the entire cross-section of a member. And when I refer to the cross-section, I'm talking about the view of the member when you look at it from the end. So the square shape that you see here is the cross-section of the member. Stress is internal force distributed over that cross-section. So it's always expressed in terms of force per area. For example, pounds per square inch or newtons per square meter. It's really the same as a pressure, the sort of pressure that you experience when you check the pressure in the tires of your car. Stress is a really important concept because the strength of a material is defined in terms of characteristic values of stress. For example, a standard grade of structural steel fails at a stress of 36,000 pounds per square inch, PSI. So 36,000 PSI is the strength of this material, its characteristic failure stress. Okay, so the final step in our roadmap is to evaluate the performance of the structural element by comparing stress against strength. If stress is greater than strength, then the material is going to fail. If the stress is less than the strength, then we could expect no material failure and the structure is going to be able to carry load safely. This evaluation is the ultimate goal of structural analysis. And that's our basic roadmap. And I really have to add that it's a significant simplification of the real-world considerations in structural analysis. Practicing engineers are actually concerned with far more than just stress as a measure of performance. For example, deformations are also a major consideration in the design of most structures. But for our purposes in this course, this is a good starting point. The map will get us where we need to go in paradise. And most importantly, the map equips us to answer a question that is absolutely essential to our purpose in this course. What does it mean for a structure to carry load? We can now see the answer to this question right here in the roadmap itself. A structure carries load successfully if the stresses that are caused by external forces are less than the strength of the associated material. Okay? So that's our roadmap. Now let's return to the start of that process, the start of this conceptual model of how structural analysis is done, and take a closer look at the external forces, the loads and reactions. And to make that concept of a reaction a little bit easier to see, what I'd like to do is return to our model of the Chuteau Bridge. What we're going to do is replace the physical supports with devices that will allow us to measure the reactions directly. Now we've replaced the supports with scales, which will allow us to directly measure the reactions. I'm going to place the bridge onto the scales. Remember that the bridge weighs 2 pounds, and as you can see from the readings on the scale, makes sense. The 2-pound bridge caused the scale to register 1 pound on one side and 1 pound on the other. Now I'm going to replace that live load that was applied at midspan, and remember the live load weighs 3 pounds. And just as you might expect, when I add the 3-pound load, each of the two reactions increases by half that amount, 1.5 pounds. So we now have a total of 2.5 pounds of reaction on this side, 2.5 pounds of reaction on the other side. And guess what? It all adds up. The total downward load is the weight of the bridge, 2 pounds, plus the additional 3-pound live load. That's a total of 5 pounds. The total upward reaction is 2.5 plus 2.5, also 5 pounds. All of the forces acting on this system are in balance, and therefore the system is said to be in equilibrium. And this principle, the principle of equilibrium, is without question the most important concept in all of engineering mechanics. As best we know, the first person to discover and publish the principle of equilibrium, as we understand it today, was a brilliant Flemish Renaissance-era mathematician named Simon Stevin. In 1586, Stevin demonstrated this principle with an ingenious proof, which is shown here. This is a kind of a thought experiment consisting of a string of evenly spaced circular beads draped over an inclined plane. The gist of the proof is that the larger number of beads on the shallower slope exactly balances the smaller number of beads on the steeper slope. And this shows how forces in equilibrium balance each other out. Now, this particular proof really isn't critical to the course, but I just had to show it to you because someday you're going to visit the beautiful city of Bruges, Belgium. And while you're there, you're going to walk just a few blocks south of the main marketplace in the middle of town to Simon Stevin Square. Yes, there is a Simon Stevin Square in the middle of Bruges, and there you'll find this statue of the great man. And in his hand, you'll see a parchment bearing the very diagram we just talked about, the world's first proof of the principle of equilibrium. There are many beautiful things to see in Bruges, my friends, but none so beautiful as this. Although Simon Stevin's work was groundbreaking, though, it really had little immediate impact either on the world of science or on the world of engineering, possibly because Stevin published only in Dutch, and Dutch wasn't spoken widely outside of the Low Countries, but also probably because Stevin was so far ahead of his time. 100 years later, though, the time was right. And in 1687, the great Sir Isaac Newton literally changed the world with his publication of the Mathematical Principles of Natural Philosophy, or Principia for short, one of the most influential works in the history of science. Newton's Principia included his 3 laws of motion, which form the foundation of modern engineering mechanics even to this day. Over the next few lectures, we'll be using all 3 of Newton's laws to help us understand great structures. But today we want to focus on just the first law. An object at rest will remain at rest unless it's acted upon by an unbalanced force. Let me try stating that a little bit differently and more usefully for our purposes here. If an object is at rest, then all of the forces acting on it must be in balance. So, what does it mean for forces to be in balance? To help us explore this question, I'd like to introduce an important graphical problem-solving tool called the free body diagram. This tool helps us guide our quantitative solutions to equilibrium problems, but perhaps more importantly, it helps us see the fundamental characteristics of the systems that we'll be analyzing. We'll be using it often throughout the course. And so what I'd ask is, as I talk through the creation of the free body diagram, you might want to consider drawing one yourself. It's a great way to experience Isaac Newton's ideas quite directly. And to help you along, I'm going to simulate drawing a free body diagram of my Chuteau bridge model in its current loading configuration by actually building the diagram on screen, one graphical element at a time. We'll start with the object of interest itself. That's the bridge. We isolate it from its supports. We remove the physical supports in order to cause the bridge to now become a free body. That's why it's called a free body diagram. Now we're going to draw all of the forces acting on the body. We're going to work systematically to ensure that we cover all the forces, that all the forces are accounted for. We'll begin with the 2-pound load that's applied to the structure right there in the center in midspan. And of course, that's the dead weight of the structure, the self-weight, and so it's oriented in the downward direction. Next, we want to add the 3-pound live load corresponding to the weight of the locomotive crossing the bridge. Again, that's applied at midspan and it's oriented in the downward direction. And as we just learned through our experiment involving placing the bridge onto the two scales, we also have two 2.5-pound reactions, and they're oriented upward out at the ends of the bridge. Now all we need to do to complete the free body diagram is to add some dimensions. The bridge is 4 feet long, and we want to show that the two loads are precisely located in midspan, so we'll show those two 2-foot dimensions. Now, it's pretty easy to see from this diagram that all the forces acting on the body are, in fact, in balance. We have a total of 5 pounds down. We have a total of 5 pounds up. And this sort of qualitative equilibrium analysis is quite simple because all the forces happen to be acting in one direction, and that's the vertical direction. But what would happen on our model of the Chuteau bridge if the train that was crossing the bridge suddenly slammed on its brakes? That would have the effect of applying a strong horizontal load to the structure. So when the train slams on its brakes and delivers that horizontal load, something has to prevent the bridge from sliding sideways like this. And of course, that something has to be an additional reaction that has to be developed at the supports of the structure. So clearly an additional reaction is required, and we need to show that on our free body diagram. Here's that additional 1-pound horizontal load, again applied by the train slamming on its brakes, and here's the 1-pound reaction applied at the far support in the opposite direction, counterbalancing the 1-pound applied load. This little demonstration shows that having all forces in balance on a body means that we actually have to separately consider forces in the horizontal and vertical directions. We have to consider them independently of each other. All forces in the horizontal direction have to be in balance, and all forces in the vertical direction also have to be in balance. They're two independent conditions for equilibrium. But now what happens if the locomotive moves to some other point along the length of the bridge? Suppose I move this 3-pound load from midspan out to, say, the 1/4 point along the length of the span. What does your intuition tell you about how the reactions are going to change in response to that change in the position of the load? I won't change the magnitude, just the position. What does your intuition tell you? Will the reactions change? If so, will they get larger? Will they get smaller? What do you think? Well, let's give it a try and see how it works. Remember that the current reactions are 2.5 pounds on each scale. When I move the load out to the 1/4 point along the length of the span, what we see is that the reaction closest to the load increases from 2.5 pounds up to 3.25, whereas the reaction at the opposite end, farther away from the load, drops from 2.5 down to 1.75 pounds. Interestingly, the two reactions still add up to 5 pounds. So the vertical balance of forces has actually been maintained. But how can we explain this change in the relative magnitude of the two reactions when all we did was change the position of the load, not the magnitude of the load itself? Well, the answer to this question is that there's actually one more independent condition for equilibrium in any body. If you remember when I had the load applied at midspan, The reactions were in balance. If I actually try to pick the bridge up from the center in this condition, the effect of the load applied at midspan is simply to pull downward, to resist my attempt to lift up the bridge. But when the load is off-center, notice that if I try to do the same thing, if I try to lift up the bridge from the middle, now we see that the off-center load is causing a tendency to rotate the bridge. It's really important. That tendency of a force to cause rotation has a name. It's called the moment of a force. In some disciplines, it's actually called a torque. But we're going to stick with the term moment or moment of a force because this is the term that's more commonly used in engineering. Now, a moment of a force is simply force times distance. If I hold my 2-pound weight out at arm's length, the force causes a moment, a tendency to rotate my arm counterclockwise about my shoulder. That's what a moment is, a tendency to cause rotation. Notice my arm isn't rotating, it's just tending to rotate. Let's depict that same situation graphically. Here it is. And notice that the magnitude of this moment is simply the force times the perpendicular distance from the force's line of action to the point of interest, my shoulder. The distance is about 2 feet. And the magnitude of the moment then is force times distance, 2 pounds times 2 feet for a moment of 4 foot-pounds. And its direction is shown as counterclockwise. It's tending to cause my arm to rotate counterclockwise. Similarly, in our Chuto bridge model, the off-center load was causing a tendency to rotate, but in that case, there actually was no rotation, no physical rotation of the body. We did see that rotation when I lifted it up, but when it's in place, the supports prevent the rotation from happening. When we moved the load, the reactions changed. What happened was these new reactions created a counterbalancing moment that prevented the bridge from rotating. And so what we can see from this example is that there's actually another condition for equilibrium, an additional implication of Newton's first law, if you will. Not only must all horizontal and vertical forces on the body be in balance, but all moments must be in balance as well. That situation is described mathematically here on this slide. And if this notation is unfamiliar, recognize that it's really just a shorthand, efficient way of describing the balance of forces for an object that happens to be in equilibrium. The Greek letter sigma that you see on the left-hand side is really just a symbol that means a summation. The letter F refers to forces. The subscript X refers to the horizontal direction. Y refers to the vertical. M refers to moments, and the subscript P refers to the moment about any point on the body. And so what the equations tell us is simply that if a body's in equilibrium, the sum of all forces acting on the body equals 0 in the x direction. The sum of all forces acting on the body in the y direction equals 0. And the sum of all moments about any point on or off the body also must equal 0. All three of these equations must be true if the body's in equilibrium. Let's see how this amazingly powerful set of equations can be used to predict the response of a structure to load. And let's use the specific example of our model of the Chuto bridge. Let's assume for the moment that those two reactions that we just saw on the scale are currently unknown. Can we use the principle of equilibrium to actually calculate what those reactions should be? Well, let's give it a try. We'll start our solution by following through with the process that we always do when we solve an equilibrium problem. In this case, all we really have to do is modify our existing free body diagram, shifting the load to show its new off-center location at the 1/4 point along the length of the span. We've also now shown the reactions as unknown quantities, R sub L, that's the reaction on the left-hand side, and R sub R, the reaction on the right-hand side. With this free body diagram complete, we're now ready to investigate the balance of forces using our three equilibrium equations. And as we do this, I suggest that you think of the equations as a bookkeeping tool that really just helps us keep track of forces and moments. It's really nothing more. In this particular analysis, we don't even need to use one of the three equations, the sum of forces in the x direction, because there are no forces on the body in the x direction. So we can start our solution by writing equilibrium equations for the sum of forces in the y direction. We do that summation systematically, working from left to right. We start by showing the sum of forces in the y direction equals 0. we assume that upward is the positive direction. And here's that equilibrium equation. All we did was account for each force. RL, the reaction at the left-hand end, is upward, so it's shown as positive. The 3-pound and 2-pound loads are in the downward direction, so they're shown as negative. And the unknown reaction on the right-hand side is also upward. We can do a little bit of algebra and determine, just by doing some algebraic manipulation, that the sum of those two reactions must be equal to 5 pounds. And in fact, that makes perfect sense. It's exactly what we saw in the physical model. No matter where we move the load, the reactions added up to 5 pounds. Now we have to use our third equilibrium equation, the moment equation, to attempt to actually calculate the values of those reactions. If the body's in equilibrium, then the sum of all moments acting on it about any point has to be 0. We can select any convenient point to use as the basis for this calculation, and so we're going to use the left-hand end, annotated as point P on my free body diagram. And here's what that equation of equilibrium looks like. I won't talk through it in detail. I really just want to point out that each term in the equation is the force multiplied by the corresponding distance from the point of interest, the point P, to the point of application of that load. Clockwise moments are shown as positive, and counterclockwise moments are shown as negative. And when we apply the algebra to calculate the results, we find that the right-hand reaction works out to be 1.75 pounds. We can now return to our equilibrium equation for the sum of forces in the y direction, substitute that value back into the variable for the right-hand reaction, and solve for the unknown force in the left-hand reaction, and that turns out to be 3.25 pounds. And to quote Archimedes, eureka! This is exactly what we see in our two scales. So in case you had any doubts, the principle of equilibrium actually works. Congratulations on having completed what very well may be your very first quantitative solution to an engineering problem. I hope you're beginning to see that the quantitative application of scientific principles can help us see structure in new and exciting ways. In this lecture, we developed a roadmap that depicts how a structure is analyzed. And we focused on that first step in the roadmap. Next lecture, we'll visit all of the remaining destinations on the roadmap of how to analyze a structure, and we'll see that the principle of equilibrium that we just talked about also has important implications beyond external forces. In doing this, we'll equip ourselves with all the tools we need to see and understand structure in the world's greatest buildings, bridges, and towers. Thank you.